Hello everyone, welcome to the session of Theory of Computation or Formal Languages and Automata Theory. In today's session, we discuss about the computability, where we discuss about the computational problem and how that computational problem can be divided into various types. Okay, then we will see what is the difference between decidable and undecidable problems. Okay, and then we will also discuss about the concept of halting problem. Okay, so these are the concepts that we are going to discuss in this today's session. So let us start our discussion with this computability. So generally, uh, here we are considering that a computational problem can be either a solvable one or unsolvable one. That means a computational problem can be divided into either solvable or unsolvable. Okay. So generally, when we can say that a problem is solvable, okay. So generally, this word solvable is itself explaining the meaning. Whenever we have a problem P, and for that particular problem, if there exists a solution, then that problem is considered as a solvable one. Okay. Another case is that if you are having a problem P and we can prove mathematically that the problem cannot be solved, then the problem P is also considered as a solvable one. Okay, so remember 2 points. The first point is the default that for a particular problem, if there is a solution, then that problem is considered as a solvable one. Okay, the another case is that if a problem is there and you can prove that that particular problem is not solvable, then that problem is considered as a solvable one. Okay, so this concept we have seen in the previous session when we discussed the concept of Königsberg bridge problem, right? So we have seen this problem in the previous session, and we uh, came out with a conclusion that this problem was solved by Euler by saying that this problem cannot be solved because of odd degree of the nodes. Okay, and Euler proved that this problem cannot be solved, okay, by applying the concept of graph theory. Okay, so the moment when Euler mentioned that this problem is not solvable, then the problem came into a solvable category. Why? Because the problem is not solvable. It was proved mathematically by the Euler. So, since this problem cannot be solved further and it was proved mathematically, so this problem will be considered as a solvable one. Okay. So, to relate this concept, I have used this example. Okay, so I think now you got a clear idea about the solvable problem. Okay, so there are two conditions that we have to consider. If there exists a solution for a problem, then that problem is solvable, or we can mathematically prove that the problem is not solvable, then the problem is considered as solvable one. Okay, so next one is unsolvable. Okay, next, unsolvable means the problem for which there exists no solution or algorithm will be considered as unsolvable problem. Okay, that's it. So this is the concept which we have seen in the previous session where I tried to explain the concept of solvable problem with the example of Königsberg bridge problem. Okay, so to make you understand about the solvable problem, I have taken this example. Okay, so if we consider generally the problems can be divided into either solvable or unsolvable. So solvable, we have seen that for these problems there exists a solution or there was a mathematical proof that these problems are not solvable. So they comes under this solvable category. If the problem is not solvable, that means if there exists no solution for a particular problem, then that problem will be considered as an unsolvable one. Okay, so if we observe in the olden days, all the problems were considered as unsolvable, right? Because at that point of time there was no technology. Okay, so as the technology evolved, all the problems which were there in the unsolvable came into the category of solvable one. Okay, so still there were many problems which are there in the unsolvable. Okay, so as the technology progress or new techniques were discovered, then these unsolvable problems definitely uh, become a solvable one. Okay, so if we consider that mobile phones, so in 17th or 18th century, no one has imagined the world with a device like mobile phone. Okay, so in those days, those operating the mobile devices will be considered as unsolvable, right? So as the technology progressed, many programming language came up, and uh, we could able to imagine the devices that can that can be considered as a portable one and that provides the internet connectivity. So now those mobile phones will be considered as a solvable one. That means they came from unsolvable to solvable one. Okay. So this is generally these are the problems which will be considered as solvable and unsolvable. Okay. Next one, the solvable problems can be further divided into two categories: decidable and undecidable. Right. So what is meant by decidable problem? So a problem is said to be a decidable if there exists an algorithm and procedure for that problem. Okay. So a problem P will be considered as a decidable one if there exists an algorithm and procedure for that particular problem. Okay, when we can say that a problem P is undecidable, a problem P is undecidable if there exists only the procedure. Okay, so this is a time to discuss about the difference between algorithm and procedure. So algorithm is nothing but it is going to have some finite time. Okay, so we can able to predict, or it is going to have some finite amount of time. That means the algorithm will take some finite amount of time to execute. Okay, and after that finite amount of time it is going to give an output, right? So it is going to have finite set of instruction, and it is going to take some finite set of finite amount of time to produce the output, right? So that is about the algorithm. If you consider the procedure is going to have the set of instructions, but we cannot predict the execution time of the procedure. Okay, so that is the difference. So algorithm, there is a finite set of instruction, and also there is a finite amount of time. That means it takes some finite amount of time to execute, whereas in the procedure we cannot predict the execution time. Okay, so that is the major difference between the algorithm and the procedure. Okay, so here a problem P will be considered as the decidable problem if for that problem P there exists an algorithm and procedure. A problem P will be considered as undecidable problem if there is only a procedure for that particular problem, or there is a procedure to solve that particular problem. Okay, and if we don't have an algorithm, then that particular problem will be considered as undecidable problem. Okay, so let me say factorial, right? To compute the factorial of a given number. Yes, of course. If you give a n value as 4, you could able to write a program, okay, or algorithm that could execute for some finite amount of time and produce the factorial of a n value. Okay, so that is about the decidable problem. Undecidable means finding the prime number from 100 to infinity. Okay, so finding the prime numbers from 100 to infinity, right? So this is called as undecidable problem, right? So here we are going to have a procedure. That procedure will never halt. Okay, so it will never halt. So it is going to take infinite amount of time, so we cannot able to predict the execution time that could generate that prime numbers from 100 to infinity. Okay, so this problem will be considered as something like undecidable problem, right? So the factorial program, it is going to take some finite amount of time to execute, and definitely it will gives an output, right? So but in undecidable we are going to have a procedure but uh, we can't predict, that means how much amount of time it is going to take. Okay, next one. So this is nothing but decidable. This is the point that we have seen. There are the problems for which there exists an algorithm and procedure, and we can predict how much time it is required to solve a problem. So these two properties are related to this decidable one. And next one is undecidable problem. These are the problems for which there exists a procedure to solve them. Okay, and we don't know how much time it takes to solve the problem, right? So as I mentioned that the procedure will be there, but when you execute that procedure, we cannot predict the execution time for it. Okay, so that is about the decidable and decidable problems. Okay, so let us have a look on this difference between the recursive language and recursively enumerable language. So here we could say that a language capital L is a recursive language if there exists a Turing machine which will accept all the strings that belongs to L and reject all the strings that does not belongs to L. Okay, so what it means, a language L is said to be a recursive language for which there exists a Turing machine. Okay, so for all the strings that belongs to L, the Turing machine is going to accept those strings which are there in the language, and for all those strings which are not in the language, the Turing machine is going to reject. Okay, so that is the one point. And next point is that in this case the Turing machine compulsorily halt. Okay, either by accepting the input or by rejecting the input. Okay, so Turing machine will always halt either by accepting or rejecting the given input string. Okay, and next point is that recursive languages are closed under all the operations except homomorphism and substitution. Okay, so substitution, as we know that symbol of a particular language will be replaced by symbol of another language, right? So that is called as substitution. So recursive languages are closed under all operation except the homomorphism and substitution. Okay. So these are the three important points that you have to remember for this recursive language. Okay. And one point that you have to remember for the closure properties. Okay. The recursive languages are closed under all operations except homomorphism and substitution. Okay. Next one, recursively enumerable language. The language capital L is said to be recursively enumerable language if there exists a Turing machine which accept all the strings in L and halt. Okay, so for all the strings which are there in a language L, all those strings are going to be accepted by the Turing machine. Okay, so the Turing machine halts and accepts all those strings which are there in the language, right? So another possibility is that for all the strings which are not in the language, the Turing machine may or may not halt. Okay, so for example, if you give a input W which does not belongs to L to a Turing machine, then the Turing machine may halt or may not halt. Okay, so halt means it may halt at some state and gives the result as reject. Okay, and it rejects the string. Or for some strings which does not belongs to the language, the Turing machine may enter into the infinite loop, right? So this is the recursively enumerable language. So recursively enumerable languages are closed under all operations except set difference and complement. Okay, recursively enumerable languages are closed under all operations except set difference and complement. Okay, so this is the diagram for the Turing machine for the recursive languages and recursively enumerable languages, right? So if you consider the recursive language, so if you give a string W which belongs to L, then the Turing machine halt and accept the string. Okay, so you could imagine like that whenever you give a string W that belongs to L to a Turing machine, it halts in a final state. Okay, so when it halts in a final state, it will be considered as, that means the string will be considered as accepted. Okay, if you give a string W that does not belongs to L, then the Turing machine halt and reject the string. Okay, so here the possibility, there are two possibilities: halt and accept, halt and reject. So halt and accept, that we will get if we give the string w that belongs to a language L, that means that belongs to a recursive language, right? So next possibility is halt and reject. So this situation occurs when you give a string W that does not belongs to a recursive language L. Okay, so these are the two possibilities, right? And for a recursively enumerable language, the Turing machine may halt and accept, okay, or halt and reject, or loop forever. Okay, so if you give a string w that belongs to the recursively enumerable language L, then the Turing machine definitely halt and accept. Okay, if you give a string that does not belongs to L, then Turing machine may halt or may not halt. Okay, so it halt and reject the string if w does not belongs to L, or it may enter into the infinite loop for the given string w that does not belongs to L. Okay, so here we are having three possibilities, right? So in recursive language we are having two possibilities where Turing machine doesn't enter into the infinite loop. Okay, but in case of recursively enumerable language, there is a possibility that the Turing machine may enter into the infinite loop. Okay, so these are the difference between the recursive and the recursively enumerable language. Okay, next one. So let us discuss about the decidable and undecidable language, right? So what is a decidable language? A language capital L is decidable if it is recursive language. Okay. So definitely recursive languages are decidable languages. Okay. So all decidable languages are recursive languages and vice versa. Okay, so the same point. So language capital L is decidable if it is a recursive language, right? So we have seen that a recursive language means there exists a Turing machine that uh, takes the string w of capital L and accept it, okay, and halt it. And whereas if you give a string that does not belongs to the language, then Turing machine halts and reject that particular string, right? So if that property are satisfied, then that particular language will be considered as a decidable language, right? And next one, partially decidable language. A language capital L is a partially decidable if capital L is recursively enumerable language. Okay, so a capital L will be considered as a partially decidable language if capital L is a recursively enumerable language, right? So here the Turing machine may or may not halt, right? So for a given input string W, the Turing machine may or may not halt. Okay. So here, due to this property, we are saying that the language is partially decidable. Okay. So there is a no determinism where we could say that for this particular string, the Turing machine halt, or for this particular Turing machine, it accept or it reject, like that. Okay. And next one, undecidable language. A language L is undecidable if it is not decidable. Okay. So if it is not decidable, then that particular language will be considered as undecidable. Okay. And one more property here is that an undecidable language may be partially decidable but not decidable. Okay. So undecidable language could be either partially decidable or it will be considered as undecidable one. Okay. If a language is even not partially decidable, then there exists no Turing machine for that a language. Okay, so generally, uh, if a language is not a partially decidable, then for that language we could not able to construct the Turing machine, right? So when we cannot able to construct the Turing machine for a particular language, then it is going to be considered as undecidable language. Okay, so that is the point. So here there is a description which is mentioned in a form of a table here. The recursive language, for recursive language there exists a Turing machine that always halt. Okay. Recursively enumerable language, there exists a Turing machine that may or may not halt. Okay. And next one, decidable language. Recursive languages are considered as a decidable language. Partially decidable language, these are recursively enumerable languages. Okay, so partially decidable language is nothing but recursively enumerable language, and undecidable language means there exists no Turing machine for such languages. Okay, So whenever we cannot able to construct the Turing machine for a particular language, then it will be considered as undecidable language. Okay. And next one, coming to this one, halting problem. So what is a halting problem? So generally it is a question. Okay. So halting problem is a question, right? So what is that question? So question is that if there is a program P and input, and if there is a program and input, okay, can we predict whether that program halt or run forever? So consider that you have given with some a program and with a input. Okay, so you need to tell whether that program halt or enter into infinite loop. So this is the question which we can consider as an halting problem, right? So we cannot say whether that particular program will halt or may enter into the infinite loop. Okay, so we cannot mention that, or we cannot specify that with a proof. So we could say that that particular problem is considered as a halting problem, right? So in order to uh, specify, or in order to uh, answer that particular question, we need to test that particular program, right? So whenever we have some program with along with some input, and we are asked to tell whether that program will halt or run forever. Okay, so to come out with a particular answer, what we need to do here is we have to test that particular program. Okay, we have to run that particular program, then only we can able to answer whether it is going to give an output or going to enter into the infinite loop. Okay, so this particular problem will be considered as a halting problem, right? So we cannot able to design a particular program. Okay, we cannot able to design a particular program that takes the program, some program P, and input I, and predict whether that particular program P halt or run forever. So we cannot able to design an algorithm, right? So that's why this particular problem will be considered as a halting problem. Okay, and this problem is undecidable. Okay, so because we, for a given program along with an input, we cannot identify whether that program gives an output or it enters into the infinite loop, or we cannot able to design an algorithm that uh, checks that property. Okay, so that's why this particular problem will be considered as undecidable problem. Okay, so here given a Turing machine, whether a Turing machine halt for some given input, so this is the question. Okay, or it may enter into the infinite loop. So this is the same. So just we are relating a problem with a Turing machine, right? So given a Turing machine, okay, along with some input W, whether it halt or enter into infinite loop. So this is the question, and this question is considered as a halting problem. Okay, so what is the input that we have to give? The input could be Turing machine and along with input string W. Okay, so does Turing machine halt for a given string W in finite amount of time? So whenever we are given with a Turing machine and with a input W, and we are asked to tell whether that particular Turing machine halt or enter into infinite loop, so we cannot able to specify the answer correctly. Okay, we cannot predict the answer correctly whether it halt or enter into infinite loop. Okay, so that's why this particular problem will be considered as a undecidable problem, right? So we cannot able to construct a Turing machine, we cannot able to construct a Turing machine that takes the Turing machine and input W, and specify whether that particular Turing machine for that W, given input W, may halt or enter into the infinite loop, right? So that is the thing that we cannot uh, perform with the Turing machine. Okay, so here uh, This problem will be considered as a halting problem. So here, this is the same one. Given some program with some input, will it ever get into infinite loop or will it halt? Uh, that means we cannot able to design a program which performs such type of testing. Okay, so that's why this is undecidable problem. So here we can say that it is undecidable problem. So no Turing machine can be designed for the halting problem, right? So you may get a question related to this halting problem. Okay, short answer question. So yes, you need to mention the statement, and if possible, you could draw this diagram. Okay, so here we are having a Turing machine that takes the input W. For that W, the Turing machine may or may not halt. Okay, so if W belongs to the language, then the Turing machine may halt. Okay, if it does not belongs to the language, then Turing machine enter into the infinite loop, right? So this thing that we cannot predict by designing the another Turing machine. Okay, so this is the thing. Okay, so in today's session we discussed about what is this computation, okay, and how that computation problem is divided into this solvable and unsolvable, okay, and then what is the difference between decidable and undecidable problem. Then we have seen the difference between algorithm and procedure. So for decidable problem there exist only the algorithms, okay, and for undecidable problem there exist only the procedure, okay. And next one is we have seen what is the difference between decidable language and undecidable language, right? So, and we have seen what is partially decidable, undecidable, decidable languages, and then we have seen this halting problem. Okay, so these are the important topics that we have to remember for your examinations. Okay, so you may get a short answer questions on these topics. Okay, so in the next session we will discuss about the undecidable problem, that is post correspondence problem and modified post correspondence problem, and we will discuss about this uh, P, NP, NP complete, NP hard classes of the problems. Okay, so we will discuss those things in the next session. So that's it for today's session. Just revise these concepts. Okay, if you feel any difficulty, just notify me once. I will try to answer those questions in the coming sessions. Okay, so thank you.